The perceptron works really well, except when the data is not separable. When we have noise in the data, we keep updating the weight vectors. We keep moving our boundary back and forth. One solution to this problem is to average the weight vectors over time. This generally improves the performance. Another issue with the perceptron is that some boundaries are clearly better than others. So how do we pick the boundary that gives us a better generalization as opposed to this one here that barely separates the data? So one idea is to adjust the weight update to mitigate these problems. So let's say we start with this green line as our boundary, and we pick one example. So instead of updating our weights and pushing our boundary all the way over there, we try to choose an update size that fixes the current mistake but minimizes the change to the weight vector. So instead of this new boundary here, we pick this one, the one that barely fixes the problem, that barely fixes the mistake. This technique is called MIRA, margin-infused relaxed algorithm. So to implement MIRA, we introduce a learning rate. So instead of subtracting or adding the feature vector to our weight vector, we add or subtract a fraction of it. This fraction is our learning rate, R, and note that R here depends on the example because we want R so that the update causes the example to be labeled correctly. We want to fix the error, but we want to also minimize the difference between the new weight vector and the old weight vector. So this R here is going to be computed for each example. We can basically write the equations. We have one equation that says we need to fix the mistake. We need to update the weights so that f of x is labeled correctly. And on the other hand, we need to minimize the difference between the new weights and the old weights. So solving for these equations, we're not going to go over the details here, but that gives us the learning rate for MIRA here. Now, there are times when the minimum correcting update is still too much. Let's say the example was labeled incorrectly. So we have this negative example here in the positive region. So if we were to update our weights just enough so that this example falls in the negative region, we'll have to move our boundary all the way over here. Finding the minimum correcting update that will result in this example being classified correctly will still push our boundary all the way over here and cause most of our positive examples to fall in the negative region now. The solution here is to cap the updates with some constant. So we can only update our weights this much at each step, even if our example is still classified incorrectly. This approach converges faster than the perceptron, and it usually works better, especially on noisy data. There is one more thing that we can do to improve our classifier. Let's say we have red examples and blue examples here. These are clearly separable. So our perceptron picks one example at a time and learns from it and eventually converges to a boundary. Now, depending on the order of these examples, our perceptron could converge to any one of these boundaries here. All these boundaries classify all the training data correctly, but which one is better? Our intuition tells us that the best boundary is the one that goes right in the middle between the red and blue regions. So this idea leads us to support vector machines, or SVM. Here, we want to maximize the margin. We want to find the boundary that has the largest gap between points on either side. Note that only those examples on the margin count here. Other training examples do not matter here. So this is the basic idea behind SVM support vector machines. Let's take a step back and compare the two classification algorithms that we have seen so far. The first classifier we've seen was naive Bayes. In naive Bayes, we built a model from our training data. We were able to compute prediction probabilities based on this model. We made strong and naive assumptions about feature independence, and the classifier made only one pass through the data. Each example was examined only once. The perceptron, on the other hand, makes fewer assumptions about the features or the data. It is a mistake-driven approach to learning. There are multiple iterations here, multiple passes through the data. The perceptron is often more accurate than naive Bayes.